Today on the bench is my Hewlett-Packard 606A signal generator, and this I've had for quite a few years, and it's probably been 20 years since I last used it, so it's really getting to a point, well past a point in fact, of needing capacitors checked at least and potentially replaced. Also, I've found that just an initial inspection, the range selector switch is frozen. The main dial is also quite frozen, but you can move it with the vernier, so there's some lubrication required in there, and supply across the line caps and electrolytics will probably go before we switch it on and do some tests on it. But other than that, it's been in storage, as I said, for about 20 years, and apart from a few scratches on the actual top paintwork and the sides and whatever, the front panel is in great condition and just needs a general clean up. If I remember correctly, I have had it open in the past and it's pristine inside. From the serial number, prefix is 434, so basically that should be the 34th week of 1964 that this was manufactured, so it's probably about halfway through the run, or a bit past the middle of the run of the 606A before it changed to the 606B. So next step is to open it up and have a bit of a look inside. With the back cover off, we can see this is the mains input cable that plugs into the line filter here, and this line filter is going to have to come off because the across the line caps in here need to be changed out with safety caps. The caps in here are probably pretty tired and leaky, so that's the first step before we do anything else. Here you can see the two across the line capacitors. They connect, each one connects to one side of the line and to ground, and they look clean, look almost pristine. They have a hard plastic case to them, so there shouldn't be any moisture ingress causing an issue. However, these are, according to the manual anyway, a paper capacitor, and I'd rather put in a modern safety capacitor in their place just for my peace of mind. Also, while I'm doing this, there's the insulation on this mains cable is a bit bowed up here, and it looks like it could crack fairly soon, so I'll replace the mains cable in this as well, just to make sure that everything is as safe as it can be. Just did a quick continuity test and found that whoever wired this plug when this equipment came to Australia, they've wired it backwards. We've got white wire here, which is American neutral, and the black being the line, and they've actually swapped these over because active in Australia is on the left hand side and neutral is on the right hand side, so they've swapped active and neutral. And while in this equipment it's not so much of a problem with the fact we've got an isolated mains transformer in the equipment, it's the fact that you're switching the neutral, and if you're working on the equipment with it plugged in and you've got covers off and whatever, everything to do with the primary of the transformer potentially is a shock hazard. So apart from the fact that I was going to replace this mains cable anyway, I can see now too that this needs to be fixed as well. As part of the overall evaluation and testing prior to firing up this HP606A signal generator, I have gone through and tested all the tubes in it, and interestingly I found 3 that were faulty. 2 12AT7s, which both of these have quite low emission. One was in the output amplifier circuit, and the other one was the audio oscillator for modulating the RF. The emission on those were quite low, and something that I don't see all that often is gassy tubes causing internal leakage. This one here, which was in the output amplifier circuit, that was gassy, and also this 6AW8A, which is in the output amplifier, was also gassy. However, the emission was still quite good in it, but just because of that leakage, and it potentially will progress over time, go further and further to air, they've been all removed and replaced. But as I said, I don't normally see valves or tubes go slightly gassy like this. Normally, if they've got a crack in them, they've gone to air and the getter goes white, which is an obvious sign. But these don't have that. They've got leakage in the order of megohms, so it's significant, and just to mitigate any future issues, they've been replaced. For those of you that are wanting to work on one of these units, there's a good tip in the HP manual. They suggest not to start adjusting any of the internal controls if you've got an issue with the thing. To check the tubes first, then if they need replacing, then and only then readjust the internal controls associated with that part of the circuit. And the manual has quite a decent set of charts showing which tubes actually affect which adjustments, so that you can go to that particular part of the circuit and find the relevant adjustments quite easily, rather than going through a whole recalibration procedure. But it's a good tip. Don't just start adjusting things thinking you're going to fix a problem. After finding a failed electrolytic on the output of the minus 200 volt supply, I've temporarily included some new capacitors there so that I can then check all of the power supply voltages to see if they're okay. So this is now ready for me to fire up and test, and just see how we go. So as the first test, we've got it hooked up to measure the minus 200 volt, the regulated minus 200 volt supply, and I'll just turn on the current limited AC supply, and it'll start to come up slowly. And at the moment we're only drawing about 30 odd watts at 126 volts, but I'll go to remove the current limit now, and it will go up to removing current limit now, and we're up to 230 volts, and we're showing, as you can see, we're showing minus 203.3 volts. So the negative 200 volt supply is pretty good, and I'll have to now check the plus 300 volt supply, make sure that that's correct. But if we swing around here and have a look at the Crow, we've already got output from the oscillator, and in fact I can get my hand in around here. That's the attenuator, the variable part of the attenuator, not the step part, and then if we adjust frequency we can wind it back. So the oscillator appears to be working fine, but I'll still just check the plus 300 volt supply, make sure that that is all okay, and then we can start doing some little cosmetic things and doing some testing and possibly recalibration if necessary. And if we come in on one of these cathodes, you can see we've got 308.7, so the main B plus is operating fine. So next I'll have to see about the range pointer repair. On the HP606A signal generator, there is a mechanically operated pointer here that indicates which range you're selected to, and behind the main dial there is actually a cam that pushes against this piece of aluminium, and there's a retaining spring that pulls this back so that the pointer will point to the particular range. What had happened here was this had frozen up, and I could push it back and forth, but it was very, very tight. And in fact what was happening was there's a bearing here, just bring up to the camera, this bearing, which is then the metal edge is folded over onto this piece of aluminium. But what had happened was, with that shaft binding up due to hard old grease between the shaft and the bearing here, the bronze bearing, this had frozen so badly that just the action of the cam was doing two things. One, because there was a lot of force here, this has been bent out of shape, and we're going to have to realign that once everything's back in place. But also this metal here, where it's been folded over from the bearing housing, was actually slipping on the metal rather than the bearing actually moving on the shaft. And just for those of you that might be horrified, I've got a pair of vice grips. I've actually got it, there's a section on the shaft here that is at a slightly lesser diameter and not finished deliberately, so that you can actually hold the shaft without damaging the actual bearing surfaces. So that's alright. So I was able to put a big pair of pliers around here, heat this, and with the vice grips actually work this back and forth until such time as it become free, and then I've put a bit of WD-40 in there to further free it up, and it's actually quite nice now. And in fact you can actually pull it with the spring, and the pointer will go down and the cam will push this up, so the spring maintains the position of the pointer depending on where the cam is. Now with this reinstalled, you can see that the pointer properly indicates the range that it's on, and at the top range it'll go down to the bottom and start again. So now that mechanical repair has been effected, we can go on to the last few things, which is just a bit of reassembly, a bit more cleaning, and finally when some of the new filter capacitors arrive, I can finish the recapping, and then it's good to go. Just arrived are some incandescent lamps so that I can actually have a real filament type pilot lamp back in this HP606. So we'll just get to and stick the lamp in. Now we can fire this up with a genuine incandescent lamp in the front panel, and there's nothing better than a highly inefficient incandescent lamp that's appropriate for this type of equipment, not your LED rubbish. Now that the 10 microfarad 450 volt RUBYCON capacitors have arrived, I wanted to wrap up the oscillator and amplifier section of this HP606A and get the cover back on. Before I did that, this electrolytic capacitor here, multi segment capacitor is working, but testing I've done showing it is starting to show signs of leakage, albeit it's still in the early stages, but it's going to fail eventually. So wanted to replace those, and in the 606 it's actually quite easy because there's a tag strip here, and normally there are two unused pins which are ground pins, so, and they're right next to the actual connections for the capacitor, so it was quite an easy matter to actually just install new capacitors on here. And you note I've got some heat shrink on here so that we can bend the capacitors to fit nicely and not have any of the leads shorting, or down the track if there's any vibration or whatever, there's no chance of the lead shorting. So that's the amplifier and oscillator section complete. I'll just put a little bit more molybdenum grease on the vernier gear wheel, and then I can wrap this up, put the cover back on, and then we can start finishing off the changeover of the electrolytics in the power supply. A few other interesting things about this unit you may not know, probably there are plenty of you that do, but the attenuator in here is not just an ordinary attenuator. This is basically virtually the same design as a separate HP product, the 355, which came in various variants, A through to F, depending on the number of steps, the size of in dBs, the size of the step, was an attenuator from DC to 1 gigahertz, 50 ohm attenuator. And if we take a look in the side of this unit, you'll see what I mean, because I'll actually grab one of these attenuators as well to give you a comparison. So for comparison, here is an HP355D 120 dB attenuator, 10 dB steps, and here is the attenuator in the 606. And okay, you might say, oh, it's just the same box, but if you look in the manual, the circuit in this is virtually identical, and the method of switching is identical almost to this. There's a slight circuit difference, but essentially they're very much the same. So even if, and I'm not advocating this, but even if you had one of these oscillators that was junked, basically, you could actually remove the attenuator out of this and have it quite a decent attenuator up to 1 gigahertz. So the quality in this HP606 is just astounding. Another interesting thing about this is just the mechanical design that went into it. Just the fact that for stability there's a cast chassis in this unit. Given the constraints of the technology of the time, and we're talking late 50s design here, this is quite a remarkable oscillator in any way you like to consider. For stability, there was no such thing. If there was, it would have been expensive, but I don't think there was any such thing as synthesized signal generators at the time. So for stability, they went for turret tuning of the oscillator section and the output amplifier section, and there's two turrets here. And to set the ranges, you've got this whole mechanism. You'd rotate the range switch, these two turret sections counter rotate and select the current range that you require, and it's just a magnificent piece of engineering. The casting here is so thick aluminium, and it was all done for stability of operation. Having said that, the stability was not only from a frequency point of view but also an amplitude point of view, and they had feedback amplifier in the output amplifier circuit to level the output, and does maintain the level across all of the bands, and within the range of a given band does that beautifully. Everything has been done to try and minimize any influences. The power supply, for instance, is has as many tubes in it. I think I'd have to count them, but there's about as many tubes in the power supply as there is in the main oscillator and amplifier section, if you include also the audio oscillator for the modulator and the modulation section of the unit. So it was really a very good design for the time, very stable. When I fired this up after changing a few of the components, a few valves, I don't think I have to recalibrate this. The output frequency over the bands and over the range within the given band, it's pretty much spot on. Yes, it's not as stable necessarily as a modern synthesized oscillator, but considering what it is and when it was built, it is, I think, a good demonstration of excellent technology of the time. While assessing all of the electrolytic capacitors in the power supply, I found that the output capacitor on the negative 200 volt supply was faulty. Basically, capacitance was greatly reduced down to only a few nanofarads. It should have been about 40 microfarads. And the enclosure for that capacitor had two electrolytics inside it, a 40 microfarad and a 120 microfarad, both 450 volt. So that is in behind these capacitors here mounted on the chassis. So I've replaced those simply because I don't know how long the 120 microfarad capacitor is going to last, considering that the 40 microfarad has already failed, and in fact the 120 microfarad it looks like it's got a bit of leakage, not a lot yet, but it's going to fail. And I decided then, seeing we've got a problem, or had a problem with those, that the other two capacitors here, they're both, well, all three capacitors are 120 microfarad and 40 microfarad. This one here, the 40 microfarad section is not used, and this one here, both sections are used. So I decided to remove all of these from circuit and place new ones here, so that we've at least got brand new capacitors and reasonably good quality RUBYCONs, about 10 to 12,000 an hour at 105 degrees C. While I was working on this, there was a 10k 10 watt resistor that's actually bolted to the chassis here, and that goes across the series pass elements in the power supply. So all the in the positive supply, that is the 300 volt regulated supply, so all, I think it's 5 12B4s paralleled for that, and this is across those tubes, so that part of the control circuitry is always provided with some volts, even if the output series pass elements are biased off. And I only found this being an issue just by probing around with the meter, and it's open circuit. It basically, for some reason, it's failed. I don't know whether it's temperature, age, or someone's in the past shorted the supply and overloaded this resistor. I really don't know, but the circuit was working fine in that, even though this resistor was open circuit. So today I've received a replacement which is somewhat beefier. This is a 25 watt, but should just fit in place of the original. Currently, just as a temporary measure, I've got 4 47k 3 watt resistors in parallel, and they work, but the temperature rise is significant, upwards of 65-70 degrees. So I've got this 25 watt resistor, and even if you derate it for the temperature that these resistors were working at, that comes down to about 21.5 watts. And then they also in the data sheet have a deration for resistance values above a nominated value for the size of the resistor, and in this case it's 12k. So even though this is a 10k and that deration shouldn't apply, I've still applied it, and that still brings this down to about 16 watts or so at 70 degrees C. And from calculation, these resistors should be running at about 3.3 watts. Well, the total should have a 3.3 watt dissipation. So this should be well and truly capable of handling it. Should basically last for the remaining life of the equipment. This new resistor, I'm a little bit concerned about the separation distance between where the end of the resistor is fixed to the chassis, as the separation distance between this tab and the chassis is far less than with the older resistor. So what I'm doing here is, without it actually being in the equipment, I'm soldering on a section of silicone wire. This is actually rated at 1500 volts, and then I'll heat shrink this, probably 2 layers of heat shrink or so that we've got some good insulation right up to the resistor. And then I'll most likely apply some capped on tape to the surface of the chassis in this immediate area, just so that generally we've got good insulating properties in the area of this terminal. Some of you may think that this is a bit of overkill, but I've put some capped on tape, about 3 layers of capped on tape here on the chassis around the bolt hole for the power resistor, just so that we've got some extra insulation in case of any failure of the heat shrink or whatever in the future. And I always look at it from a point of view, I'd better be safe than sorry, so it just gives an extra level of protection. Okay, now the resistor is in, it's ready for reconnection, and I can remove this terminal strip that I was using for the temporary resistors. With the new power resistor installed here, we've now got 305.1, about 305 volts, and everything seems to be quite stable. As an additional check, I'll just change the range here, and we'll go to AC on auto, and that's actually showing 5 millivolts, which is about half of the spec for Ripple on the 300 volt rail. The specification is 10 millivolts, so that appears to be working fine. Also, just a quick finger test on the resistor here, and it's barely warm. It's probably slightly higher than body temperature. It's probably something of the order of about 45 degrees. I can just easily keep my finger on here. It's not hurting at all. So I'll just put my thermometer on that and just do a double check of the temperature. And it would appear my finger thermometer was pretty close. It's actually 44.9 degrees C, so I'm quite pleased about that. That resistor will be running nice and cool for the circuit, considering it's dissipating, or should be dissipating, about 3 watts. And also a quick retest of the negative 200 volt supply. We can see that it's negative 200.4, and I'll just also do a check of the AC ripple, if I can get this to, and the AC range on this meter's not sensitive enough to give me a reading, so it's possibly 1 millivolt or lower, and so that's in spec as well. Well, the HP606 is now back in its case and running, and I've just been doing a few spot checks on frequency, and it's well within the calibration range of the calibrate control here to set the dial reference. So currently on this, what I'd class as a fairly inaccurate counter display, we're seeing about 454.96 kilohertz, and it's set to 455 on the dial there. So with other tests that I've done across the bands, it seems to be functioning fine now. This can now be put back into service, albeit it's quite a large generator, but it's still worthwhile, I believe, even in this day and age.